The moon, bathed in silver light and eternal mystery, has captivated humanity for millennia. Its serene glow has inspired poets and astronomers alike, a beacon of beauty in the night sky. Yet beneath its tranquil facade lies a realm of unparalleled danger and intrigue. The permanently shadowed regions, PSRs, near its poles. These areas, cloaked in eternal darkness, harbor secrets that could unlock the future of space exploration, and perhaps the survival of humanity itself. Within these frigid, unlit craters lies the promise of water, a vital resource for sustaining life and fueling journeys to the stars. But the same conditions that make them alluring also render them perilous, presenting challenges such as extreme cold, treacherous terrain, and enigmatic phenomena. Join me as we explore the mystery at the most dangerous place on the moon. The moon's eternal shadows, the secrets of permanently shadowed regions. The moon has always been a beacon of fascination for humanity, a celestial companion whose serene beauty belies the stark, lifeless reality of its surface. Among its many mysteries, few places are as enigmatic or captivating as the permanently shadowed regions, PSRs, nestled near the lunar poles. These areas, locked in eternal darkness, are not just geological anomalies. They represent some of the harshest and most intriguing environments in our solar system. For billions of years, PSRs have stood untouched, preserving secrets that could redefine our understanding of the moon, the solar system, and perhaps even the origins of life itself. The moon's geography is a tapestry of contrasts, from its vast plains, or maria, formed by ancient volcanic activity, to its rugged highlands pockmarked by impact craters. However, it is at the poles where the most peculiar features reside. The moon's axial tilt, a mere 1.5 degrees, ensures that some regions never receive sunlight. Craters in these areas remain perpetually shrouded in shadow, their floors hidden from the sun's rays. These PSRs have existed in darkness for over 2 billion years, a span so vast that it predates most life on Earth. This unyielding shadow creates conditions that are as hostile as they are unique. The exceptionally low temperature is a hallmark of PSRs. These regions are as frigid as any in our solar system, on par with the frozen tundra of faraway objects in the Kuiper Belt. This eternal chill is caused by the lack of sunshine, which stops everything from being hot and also makes everything naturally cooler, so materials may be preserved for a very long time. Many lunar resources, including water ice, are thought to be located in these icy crevices, according to experts. Water ice in PSRs is more than a scientific curiosity. It is a key to the future of lunar exploration and colonization. Unlike the dry, desolate expanses of the moon's sunlit surface, PSRs act as natural cold traps, capturing and preserving water molecules delivered by ancient comets, asteroids, and solar wind. Over billions of years, these regions have accumulated reservoirs of water ice, a discovery that has sent ripples of excitement through the scientific community. This ice, hidden beneath a thin layer of regolith, is more than a relic of the past. It is a resource waiting to be harnessed. The significance of water on the moon cannot be overstated. For future lunar explorers, water is not just a necessity for survival, it is a foundation for sustainability. Water can be split into hydrogen and oxygen, the components of rocket fuel, enabling the moon to serve as a refueling station for deeper space exploration. It can also be recycled for drinking, used to grow food, or converted into breathable air. The presence of water in PSRs could transform the moon from a barren wasteland into a stepping stone for humanity's journey to Mars and beyond. Despite this, the risks associated with PSRs are just as appealing. Exploring these areas is fraught with danger due to the very characteristics that make them scientifically interesting. Craters, cliffs, and boulders make the lunar poles a treacherous landscape that tests the mettle of even the most sophisticated rovers and landers. Technology that can function in complete darkness and withstand sub-zero temperatures is an engineering marvel that will be required to traverse these gloomy regions. In PSRs, solar-powered equipment, a mainstay of lunar missions, is rendered useless, calling for the deployment of nuclear batteries or sophisticated thermal systems as viable alternatives. Adding to the complexity is the Moon's regolith, a fine, abrasive dust that covers its surface. This material, formed over billions of years by micrometeorite impacts, is electrostatically charged due to solar wind exposure. In PSRs, where sunlight cannot dissipate this charge, the regolith becomes an even greater hazard. It clings to machinery, damages equipment, and poses health risks to astronauts. For humans to operate safely in these environments, significant advancements in spacesuit design and habitat construction are required. Notwithstanding these obstacles, investigating PSRs holds tremendous scientific promise. These areas have preserved elements from the birth of the solar system, making them like time capsules. Potentially illuminating the processes that molded our stellar neighborhood are the water ice and volatile chemicals discovered in PSRs. Scientists are hoping to learn more about the solar system's water history and, maybe, how life on Earth began by analyzing these old reservoirs. The exploration of PSRs is already underway, with missions like NASA's Lunar Reconnaissance Orbiter, LRO, and India's Chandrayaan-1 paving the way. Chandrayaan-1's discovery of water ice in PSRs marked a turning point, confirming decades of speculation. NASA's LCROSS mission, which deliberately crashed a spacecraft into a shadowed crater, furthered this understanding by analyzing the resulting plume for signs of water and other volatiles. These missions have provided tantalizing glimpses into the potential of PSRs, but much work remains to be done. Future missions, such as NASA's Artemis program, aim to establish a human presence on the Moon's surface, with PSRs as prime targets for exploration. These missions are not just about scientific discovery, they are about laying the groundwork for a sustainable human presence beyond Earth. Technologies like autonomous rovers, cryogenic storage systems, and in-situ resource utilization, ISRU, are being developed to overcome the unique challenges of PSRs. For example, extracting water ice from the regolith requires specialized tools capable of operating in extreme cold and darkness. The timeless layers, lunar geology, and the evolution of craters. The Moon story begins with a cataclysmic event, the collision of a Mars-sized body with Earth approximately 4.5 billion years ago. This monumental impact ejected a massive cloud of debris into space, eventually coalescing to form the Moon. This violent origin set the stage for its unique geological characteristics. The Moon's crust differentiated early, creating two primary regions: the highlands, composed of ancient anorthosites, and the maria, formed by younger basaltic lava flows. These contrasting terrains bear witness to the Moon's fiery beginnings and its subsequent cooling. Craters dominate the Moon's surface, created by impacts ranging from micrometeorites to massive asteroids. The South Pole Aitken Basin, one of the largest craters in the solar system, offers a glimpse into the Moon's deep past, revealing materials excavated from its mantle. Such impacts have not only shaped the surface but also played a pivotal role in creating PSRs. These regions, nestled within craters near the poles, remain shrouded in perpetual darkness due to the Moon's minimal axial tilt, preserving ancient secrets for billions of years. The regolith, the Moon's surface layer, is a direct result of this relentless bombardment. This fine, powdery material is a mixture of pulverized rock, glass beads formed by meteoric impacts, and traces of minerals. Its composition varies across the lunar surface, with thicker layers in older regions like the highlands and thinner deposits in younger maria. Beneath the regolith lies a complex subsurface structure of basaltic layers and, in some regions, potential metal-rich deposits. This stratification offers clues about the Moon's volcanic history and the forces that have shaped its terrain. Meteorite impacts provide a unique window into the Moon's interior. When an impact occurs, material from beneath the surface is ejected, revealing previously hidden layers. By analyzing this ejected debris, scientists can infer the composition of subsurface materials, offering valuable insights into the conditions within PSRs. For example, certain impact sites near the poles have revealed traces of volatiles, suggesting the presence of water ice or other valuable resources hidden beneath the regolith. The morphology of craters holds the key to understanding their potential for harboring resources. Fresh craters often feature well-defined rims, central peaks, and terraced walls, while older craters exhibit smoother, eroded features. In PSRs, the steep walls and flat floors of large craters create cold traps, where temperatures plummet to -250 degrees Celsius, -418 degrees Fahrenheit, enabling the accumulation of water ice and other volatiles. By studying crater morphology, scientists can identify high-priority targets for exploration and resource extraction. Unique geological features within PSRs further enhance their scientific allure. The absence of sunlight has preserved volatile compounds that would otherwise have evaporated. These regions act as natural time capsules, offering a pristine record of the Moon's early history and the Solar System's volatile inventory. Comparisons with Earth's polar regions, such as permafrost zones, provide valuable analogues for understanding these cold, shadowed environments. Unlike Earth, the Moon lacks plate tectonics, allowing its surface to preserve features that are billions of years old. However, this does not mean the Moon is geologically inactive. Evidence of moonquakes, likely caused by tidal interactions with Earth or cooling and contraction of the lunar interior, suggests ongoing tectonic stress. These quakes have created fault lines and ridges, further shaping the lunar landscape. Understanding these processes is crucial for assessing the stability of PSRs and their suitability for future exploration. Another intriguing aspect of lunar geology is the presence of lava tubes, subsurface tunnels formed by ancient volcanic flows. These structures, often extending for kilometers, may provide shelter for future lunar habitats. Their potential connections to PSRs offer exciting possibilities for resource exploration and habitation, as they could serve as natural conduits for accessing subsurface materials. Dating lunar surfaces is an essential component of geological research. Radiometric dating of rocks collected during the Apollo missions has provided accurate ages for various regions. Additionally, crater counting methods, which estimate surface age based on impact density, have revealed that PSRs are some of the oldest features on the Moon. These findings underscore the significance of studying PSRs to unlock the Moon's geological history. Comprehensive mapping efforts have been instrumental in advancing our understanding of lunar geology. Missions like NASA's Lunar Reconnaissance Orbiter, LRO, have provided detailed topographical data, enabling the creation of high-resolution maps of the Moon's surface. Advances in 3D imaging and spectral analysis have further refined our ability to identify resource-rich areas, particularly within PSRs. International collaborations have played a pivotal role in these endeavors, pooling expertise and resources to create a more complete picture of the Moon's geology. Polar regions stand out for their unique geological characteristics. The regolith in these areas is often thinner and less compacted, making it more accessible for exploration. Moreover, the presence of volatiles, likely delivered by cometary impacts, distinguishes polar geology from equatorial regions. Understanding these differences is crucial for developing strategies to utilize lunar resources effectively. Lunar samples remain a cornerstone of geological research. The Apollo missions provided invaluable insights into the Moon's composition, but their scope was limited to equatorial regions. Future missions targeting PSRs aim to return samples that could reveal new information about volatile distribution, subsurface conditions, and the Moon's early history. These samples could also shed light on the processes that have preserved volatiles in shadowed craters for billions of years. The connection between lunar geology and water is particularly compelling. Crater evolution provides pathways for volatiles to accumulate, while subsurface heat may play a role in preserving these compounds. The discovery of ice and hydrated minerals within PSR craters has profound implications for future exploration and colonization efforts, as these resources are essential for sustaining human presence on the Moon. Astrobiological studies further enrich our understanding of lunar geology. While the Moon is unlikely to harbor life, PSRs may contain organic compounds delivered by cometary impacts. Studying these regions can provide a baseline for understanding planetary evolution and the conditions necessary for life elsewhere in the solar system. Solar and cosmic radiation have left their mark on the Moon's surface, particularly in PSRs. Over billions of years, the solar wind has shaped the regolith, embedding particles that preserve a record of the Sun's activity. This unique archive could offer insights into the solar system's climatic history and the interactions between radiation and lunar geology. Technological advancements have revolutionized the study of lunar geology. Ground-penetrating radar systems allow scientists to map subsurface features with unprecedented accuracy. Rovers and landers equipped with spectrometers provide in-situ analysis of regolith and bedrock, while AI-driven models help identify areas of interest. These innovations are essential for unraveling the complexities of PSRs and their geological context. The field of lunar geology has promising prospects for the years to come. Exploration missions aimed at the Moon's subsurface features and deep craters may provide hitherto unknown details about the Moon's history and habitability. Scientists are preparing the way for a new age of lunar exploration by creating maps of volatile distribution and gaining an understanding of the mechanisms that form PSRs. Unveiling the polar mysteries, historical missions to the Moon's most enigmatic regions. The exploration of the Moon's poles has been a journey marked by groundbreaking discoveries, technological challenges, and the tantalizing promise of unraveling some of the most enduring mysteries of our nearest celestial neighbor. From the early days of lunar exploration to the sophisticated missions of today, humanity's quest to understand the shadowed craters of the Moon has evolved significantly, each mission building upon the lessons and limitations of its predecessors. The story begins in the 1990s, when humanity's focus shifted from simply reaching the Moon to comprehending its complex geography and composition. NASA's Clementine mission in 1994 was a pivotal moment in this journey. Originally designed as a defense project to test technologies for ballistic missile detection, Clementine ended up providing invaluable data about the Moon's surface. By mapping the lunar terrain with unprecedented precision, it revealed the existence of permanently shadowed craters near the Moon's poles. These craters, untouched by sunlight for billions of years, offered tantalizing hints of water ice, a discovery that would ignite decades of scientific curiosity. However, Clementine's findings were not definitive, leaving open the question of whether these craters held frozen water or other volatile compounds. Building on Clementine's findings, NASA launched the Lunar Prospector mission in 1998. This dedicated effort sought to investigate the Moon's surface composition more thoroughly, particularly the polar regions. Using a neutron spectrometer, the spacecraft detected significant quantities of hydrogen at the poles, a potential indicator of water ice. Lunar Prospector's data suggested that millions of tons of water ice might be scattered across the permanently shadowed regions of the Moon's poles. However, the hydrogen detected could also be attributed to hydroxyl, a close chemical relative of water. To resolve this ambiguity, Lunar Prospector was deliberately crashed into a polar crater in the hopes of creating a plume of material that could be analyzed from Earth. Unfortunately, the experiment yielded no conclusive evidence of water ice, leaving scientists with more questions than answers. The early 2000s saw a surge in international interest in lunar exploration, with missions aiming to address the lingering mysteries of the polar regions. Among these was India's Chandrayaan-1, launched in 2008, which made a historic breakthrough in the search for lunar water. The mission's Moon Mineralogy Mapper, an instrument developed by NASA, detected the presence of hydroxyl and water molecules on the lunar surface. Chandrayaan-1's data provided the first direct evidence of water on the Moon, confirming long-standing hypotheses and reigniting global interest in lunar exploration. Additionally, the mission's impactor probe, which descended into a crater at the Moon's south pole, gathered further evidence of water vapor in the thin lunar atmosphere. Expanding on these findings, in 2009, NASA launched the Lunar Crater Observation and Sensing Satellite (LCROSS) mission. LCROSS took a daring and unconventional approach by crashing the upper stage of its launch vehicle into a shadowed polar crater, with the spacecraft following closely behind to analyze the debris plume. This innovative method confirmed the presence of water ice in the ejected material, along with other valuable volatiles like hydrogen, methane, and ammonia. The LCROSS mission was a major step forward, proving the existence of water ice in the Moon's permanently shadowed craters. On the other hand, it highlighted the complexity of these regions, as the distribution and accessibility of the ice remained unclear. Despite these successes, exploring the Moon's poles has been fraught with challenges. The extreme cold of the permanently shadowed regions poses significant obstacles for both robotic and human missions. Many spacecraft have struggled to operate effectively in such harsh conditions. For instance, Japan's Serene Kaguya mission, launched in 2007, aimed to study the Moon's surface in detail and locate water ice in shadowed craters. However, like Lunar Prospector before it, Kaguya failed to provide definitive evidence of ice deposits, highlighting the limitations of remote sensing technologies. Notable mission failures and technological challenges highlight how challenging it is to explore the Moon's poles. Several Moon missions that were supposed to research these areas have terminated too soon because of problems with technology, poor planning, or the dangers of space travel. Though disheartening, these setbacks taught us important insights that shaped how we planned and executed future missions. We are getting closer to discovering the mysteries of the lunar poles with each setback that has pushed spacecraft technology, mission plans, and scientific instruments to new heights. International collaboration has played a crucial role in advancing our understanding of the Moon's polar regions. The partnership between NASA and the Indian Space Research Organization, ISRO, during Chandrayaan-1 exemplifies how nations can pool resources and expertise to achieve common scientific goals. Similarly, other nations, including China, Russia, and the European Union, have made significant contributions to lunar exploration, each adding to the growing body of knowledge about the Moon's poles. This global effort reflects a shared recognition of the scientific and strategic importance of these enigmatic regions. Technological innovation has been a driving force in overcoming the challenges of exploring the Moon's poles. Advances in spectroscopy, thermal imaging, and impactor probes have enabled scientists to study the composition and dynamics of shadowed craters with increasing precision. However, the limitations of these technologies are evident in the difficulty of obtaining direct surface samples from PSRs. Remote sensing instruments aboard orbiters like Chandrayaan-1 and LCROSS can provide valuable insights, but they cannot fully capture the complexity of these regions. Future missions will need to incorporate advanced robotics, autonomous systems, and novel sampling techniques to bridge this gap. The lessons learned from historical missions have had a profound impact on the planning and execution of future lunar exploration efforts. NASA's Artemis program, China's Chang'e missions, and Russia's Lunar series all aim to build on the successes and failures of earlier missions, targeting the lunar poles as key sites for scientific research and potential human settlement. The discoveries made by Clementine, Lunar Prospector, Chandrayaan-1, and LCROSS have laid the groundwork for these ambitious initiatives, providing a foundation of knowledge that will guide humanity's next steps on the Moon. The search for knowledge about the Moon's polar regions is clearly ongoing as we consider the past and present of lunar exploration. Both the difficulties and the potential benefits are enormous. Undiscovered riches, important scientific discoveries, and a better knowledge of our cosmic position might be waiting for us in the perpetually shadowed moon craters. Water on the Moon, a scientific enigma. The Moon, Earth's steadfast companion, has long been regarded as a dry and barren world, a stark contrast to the dynamic planet it orbits. However, scientific breakthroughs over the past few decades have revealed that the Moon harbors one of the most sought-after resources for humanity's future in space: water. Yet this discovery is far from straightforward. The presence of water on the Moon, particularly in the form of ice, has become a scientific enigma. Its origins, distribution, and potential uses raising questions that remain unanswered. How did water, an element so essential to life on Earth, find its way to the Moon? One theory suggests that billions of years ago, comets and asteroids, natural carriers of water, bombarded the Moon during a period known as the Late Heavy Bombardment. These celestial objects, rich in frozen water and other volatiles, could have delivered significant quantities of water to the lunar surface. Upon impact, some of the water may have vaporized, but a portion could have become trapped in the Moon's surface layers or its permanently shadowed regions, PSRs, where sunlight never penetrates. The solar wind, a continuous stream of charged particles that continually batter the Moon's surface, is another fascinating possibility. Hydroxyl molecules, OH, might be formed when hydrogen ions from the solar wind contact with lunar regolith minerals that are rich in oxygen. In the ideal environment, these hydroxyl molecules may potentially undergo a transformation into water molecules, albeit in minute quantities. The intriguing possibility of producing water on an airless world like the Moon by a solar-driven chemical process is intriguing. Evidence of past volcanic activity on the Moon lends credence to these views. The Moon's early history is marked by extensive volcanism, the release of gases, including water vapor, from magma reservoirs beneath its crust. The condensation and subsequent confinement of this vapor in lunar soil or other geological formations is conceivable. The Moon's complicated history of volcanic activity adds another layer to the mystery by suggesting possible sources for some of its water. While the Moon's polar regions are often highlighted as the prime repositories of water ice, the distribution of water across its surface is far from uniform. Spectral observations have revealed trace amounts of water molecules scattered across the Moon's sunlit regions, suggesting a dynamic lunar water cycle influenced by solar radiation. At midday, when the surface temperature peaks, these molecules appear to dissipate, only to reappear during the cooler lunar night. This cyclical behavior raises questions about the stability of water on the Moon and the processes governing its movement. The Moon's PSRs, however, remain the most tantalizing sites for water exploration. These regions, located in craters near the lunar poles, have not seen sunlight for billions of years, creating environments so cold that any water ice present could remain stable indefinitely. But the PSRs also pose significant challenges for exploration. Their extreme temperatures, reaching as low as -250 degrees Celsius, -418 degrees Fahrenheit, make them among the coldest places in the solar system, complicating efforts to study and extract water ice. The uneven distribution of water across the Moon presents a scientific conundrum. Why is water more concentrated in some areas and virtually absent in others? Studies suggest that the Moon's surface texture and the composition of its regolith play crucial roles in water retention. Micro-cold traps, small shadowed depressions scattered across the lunar surface, may harbor tiny amounts of water ice, supplementing the larger reserves in PSRs. These traps, although difficult to detect, highlight the complexity of the Moon's water distribution and the need for advanced exploration tools. Detecting and mapping lunar water has been a monumental scientific achievement, made possible by sophisticated techniques and missions. Spectroscopy, the study of light interactions with matter, has been instrumental in identifying the spectral signatures of water molecules on the Moon. Missions like Chandrayaan-1 and L-Cross have provided critical data, confirming the presence of water ice in PSRs and advancing our understanding of lunar hydrology. However, these findings are only the beginning, as future missions equipped with more advanced instruments promise to refine our knowledge further. Water on the Moon is not merely a scientific curiosity. It is a resource with profound implications for humanity's aspirations in space. For future lunar colonies, water will be indispensable for drinking and agriculture, enabling long-term human habitation. Additionally, water can be split into its constituent elements, hydrogen and oxygen, to produce rocket fuel. This capability, known as in situ resource utilization, ISRU, would revolutionize space exploration by reducing the need to transport resources from Earth, thereby making missions more cost-effective and sustainable. Despite its immense potential, extracting and utilizing lunar water is fraught with challenges. Mining water ice in PSRs will require technology capable of withstanding extreme cold and operating in complete darkness. Moreover, regolith contamination poses a significant risk during the extraction process, necessitating meticulous engineering solutions to ensure the purity and safety of the harvested water. The energy demands of these operations add another layer of complexity, as establishing a reliable power supply on the Moon remains an ongoing challenge. Another topic that is now being discussed is the stability of lunar water. The Moon's surface is vulnerable to solar radiation because of its thin atmosphere, which can lead to the disintegration of water molecules and their subsequent escape into space. This sublimation process makes one wonder how long the Moon's water stores, especially in sun-exposed areas, will last. To successfully maintain and use this priceless resource, it is essential to understand these processes. Lunar water is also emerging as a strategic asset in the geopolitical arena of space exploration. As nations and private companies race to establish a presence on the Moon, control over water reserves could become a defining factor in shaping the future of space missions. The ability to access and exploit lunar water would not only confer technological and economic advantages, but also strengthen a nation's leadership in the burgeoning space economy. Scientific models of lunar hydrology continue to evolve, offering insights into the volume and distribution of water on the Moon. These models, informed by data from past and ongoing missions, help identify promising exploration targets and refine our understanding of the Moon's water cycle. Simulations of water dynamics also shed light on how lunar water reserves might change over time, providing valuable information for planning long-term missions. The implications of lunar water extend far beyond the Moon itself. By unlocking the potential of this resource, humanity could take significant strides toward becoming a multi-planetary species. Lunar water could serve as a stepping stone for deeper space exploration, fueling missions to Mars and beyond. Moreover, the discovery of water on the Moon challenges our understanding of planetary evolution, raising intriguing questions about the conditions necessary for sustaining life. Despite decades of research, many questions about lunar water remain unanswered. Could there be more extensive water reserves hidden beneath the surface? How reliable are current detection methods in assessing the depth and composition of water ice deposits? Is lunar water a finite resource, or could it be replenished over time through cometary impacts or other processes? Addressing these questions will require innovative approaches and collaborative efforts from the global scientific community. Moon water is more than simply a resource. It provides a window into the inner workings of our solar system. The mysterious substance's continuous investigation has pushed the frontiers of science and technology, opening up new avenues of inquiry and posing new problems. Navigating the shadows, conquering the Moon's most treacherous terrain. PSRs present a geological landscape unlike any other, with steep crater walls and rugged topography posing significant obstacles. These craters, shielded from sunlight for billions of years, create a labyrinth of shadows where steep inclines make navigation treacherous. Loose regolith, a fine dust covering the Moon's surface, exacerbates the risk of slippage and immobilization for rovers and landers. Hidden crevices and subsurface voids lie in wait, ready to trap unsuspecting explorers, whether robotic or human. Even identifying safe pathways in this forbidding terrain is a monumental task, demanding precise mapping and advanced navigation tools. The unique properties of lunar regolith add another layer of complexity. Unlike Earth's soil, regolith is composed of sharp, glass-like particles formed by millennia of micrometeorite impacts. These particles are not only abrasive, but also cling to every surface they touch due to electrostatic charging. This clinging nature poses a dual threat. It damages equipment and machinery while creating potential health hazards for astronauts. Inhalation of this fine dust can lead to respiratory issues, and its toxic properties are a serious concern for long-term lunar missions. Electrostatic hazards are particularly pronounced in PSRs, where the absence of sunlight alters the way solar wind interacts with the surface. Without the mitigating effects of sunlight, which can balance charges through photoelectric emission, PSRs accumulate electric charges differently. This results in areas that can be charged to hundreds of thousands of volts, posing risks of arcing and damage to sensitive electronics. Future explorers, whether human or robotic, will need to contend with these invisible dangers, which are as unpredictable as they are severe. The extreme cold within PSRs further compounds the challenges. Temperatures in these shadowed regions can plunge to a bone-chilling, making them some of the coldest places in the solar system. Such conditions impose incredible stress on mechanical components and electronic systems, which must be specially designed to withstand prolonged exposure to these frigid environments. Thermal management becomes a critical consideration, as the smallest failure could render equipment inoperable. Light and communication challenges add yet another dimension to the difficulties of exploring PSRs. The perpetual darkness means that solar-powered devices cannot function effectively, requiring alternative power sources such as nuclear batteries. Visibility is minimal, forcing reliance on advanced imaging systems and autonomous navigation technologies. Even communication with Earth becomes problematic, as the shadowed regions can block signals, necessitating innovative relay systems or satellite support. Despite these hurdles, advancements in rover technologies have made strides in addressing the challenges of PSR exploration. Modern rovers are equipped with adaptive wheel designs, allowing them to navigate loose and uneven surfaces. Autonomous systems powered by artificial intelligence enable real-time decision-making, reducing the risks posed by communication delays. Case studies, such as NASA's Viper rover and the European Space Agency's robotic prototypes, highlight the progress being made in this field. These machines are not only resilient, but also versatile, capable of scaling steep inclines and analyzing the terrain with unprecedented precision. Landing safely within PSRs remains a formidable task. Precision landing systems are essential to avoid uneven surfaces and hidden crevices during descent. The ability to target safe zones within hazardous regions can determine the success or failure of a mission. Additionally, innovative designs for adaptable landing systems are being developed to mitigate the risks associated with these treacherous terrains. While robotic exploration has taken the lead in PSRs, the eventual goal is human exploration. Astronauts face unique challenges, including the need for spacesuits that can withstand regolith abrasion and electrostatic hazards. Advanced exoskeletons or mobility aids may be required to navigate the steep and uneven terrain. Moreover, maintaining astronaut safety in such an environment will demand a combination of cutting-edge technology and meticulous planning. Case studies of past missions offer valuable insights into the successes and failures of exploring lunar terrain. Chandrayaan-3's careful navigation of the Moon's surface demonstrated the importance of robust safety protocols. Conversely, earlier missions that struggled with terrain challenges or regolith damage provide lessons on what to avoid and how to improve future designs. These experiences form the foundation for more ambitious missions to come. Robotic innovations continue to push the boundaries of what is possible in PSRs. Climbing robots and drones are being developed to access areas that are otherwise unreachable. Ground-penetrating radar is being incorporated into rovers to detect hidden crevices and subsurface voids, providing a clearer picture of the terrain. Self-healing materials and components are being explored to counteract the wear and tear caused by regolith. Power solutions for PSRs are another area of active research. Nuclear batteries offer a promising alternative to solar power, providing consistent energy for long-duration missions. Strategies for harvesting limited sunlight, such as deploying reflectors or rechargeable energy storage systems, are also being explored. These innovations are crucial for sustaining exploration efforts in the extreme conditions of PSRs. Field testing and Earth simulations have played a pivotal role in preparing for PSR missions. Simulating lunar environments on Earth allows researchers to test rover designs and navigation techniques in controlled settings. Lessons from Antarctic expeditions and deep cave explorations, which share similarities with PSRs, have also informed the development of strategies for navigating these regions. Collaboration between space agencies and private companies has accelerated progress in overcoming the challenges of PSR exploration. Joint efforts have led to the sharing of data and resources, creating a comprehensive understanding of the unique conditions in these regions. This spirit of cooperation is essential for tackling the complexities of PSRs and ensuring the success of future missions. The impact of PSR terrain on long-term lunar missions cannot be overstated. The placement of lunar bases will depend heavily on the ability to navigate and utilize these shadowed regions. Identifying resource-rich areas within PSRs is crucial for selecting sites for mining and resource extraction, which are vital for sustaining lunar colonies. Safety protocols are paramount in PSR exploration. Fail-safe systems for rovers and landers must be designed to prevent the loss of valuable equipment. Emergency protocols for astronauts navigating dangerous terrain will be essential for minimizing risks and ensuring their safety. Problems with PSRs extend beyond the physical to include operational and psychological hurdles. Astronauts' minds can take a mental toll while they navigate in total darkness, and communication delays and limited feedback make remote equipment operation much more challenging. We need creative answers and strong backbones to tackle these problems. The future of PSR exploration holds both fascinating and frightening possibilities. The way we approach these locations is likely to be transformed by innovations in lunar robots and power systems. Safely exploring and occupying PSRs is an exciting new goal for human space travel. It might lead to the discovery of the Moon's mysteries and the establishment of a permanent human presence on our neighbor to the solar system. Once seen as threats, these dark zones are today recognized as chances to grow, change, and survive in the most extreme conditions. The coldest shadows, exploring the lunar pole's cryogenic mysteries. For a very long time, the Moon, Earth's ever-present companion, has fascinated people. There is no denying the Moon's effect on Earth, from its calm, luminous appearance in the night sky to its crucial function in regulating Earth's orbit. However, the placid exterior belies a world of extremes, especially in the permanently shadowed regions, PSRs, close to the poles. These regions have experienced no light for billions of years, and hence have some of the universe's lowest temperatures. Our knowledge of survival, technology, and the limits of exploration is tested in these icy zones. This script explores the hidden world of cryogenic habitats, delving into their history, importance, and the tremendous difficulties they provide. The existence of PSRs is rooted in the Moon's unique axial tilt. Unlike Earth, which tilts at an angle of approximately 23.5 degrees, the Moon is almost upright, with a tilt of only 1.5 degrees. This minimal tilt results in certain polar craters never receiving direct sunlight, creating pockets of perpetual darkness. These craters are natural cold traps where heat cannot penetrate, and any existing warmth is radiated into the vast emptiness of space. Without sunlight to warm the surface, temperatures in these regions can plummet to an astonishing -250 degrees Celsius, -418 degrees Fahrenheit, colder than Pluto's average surface temperature. This remarkable chill has earned PSRs the distinction of being some of the coldest places in the solar system. The chilling conditions of PSRs are not solely a result of their lack of sunlight. The Moon's lack of atmosphere plays a pivotal role in amplifying their extreme cold. On Earth, our atmosphere helps moderate temperature fluctuations by trapping heat and distributing it across the planet. The Moon, however, is devoid of this protective layer, leaving it exposed to the full force of solar radiation on its sunlit side and the relentless cold of space in shadowed areas. The absence of air also prevents conduction and convection, the two primary modes of heat transfer. Instead, heat is lost exclusively through radiation, making PSRs true thermal vacuums. Comparisons with other cold celestial bodies highlight the unique nature of lunar PSRs. Neptune's moon Triton, for instance, has surface temperatures of around -235 degrees Celsius, -391 degrees Fahrenheit, but internal tidal heating from Neptune's gravitational pull prevents it from getting colder. Similarly, Jupiter's moon Europa experiences temperatures near -160 degrees Celsius, -260 degrees Fahrenheit, but benefits from subsurface oceans heated by geothermal activity. Even distant Pluto, orbiting far from the Sun, averages -230 degrees Celsius, -382 degrees Fahrenheit, slightly warmer than the Moon's shadowed craters due to its tenuous nitrogen atmosphere and seasonal heating effects. PSRs, by contrast, remain isolated and unyielding, with no internal or external forces providing warmth. The implications of such extreme cold are profound, particularly for spacecraft and instruments designed to explore these regions. Metals and materials exposed to PSR temperatures can become brittle and prone to fractures, posing significant challenges to the structural integrity of rovers and landers. Electronics, too, struggle in such conditions, as batteries lose efficiency and components fail to operate reliably. Without robust thermal insulation, spacecraft risk losing functionality soon after arrival. The cryogenic environment also affects sensitive instruments, which may require constant heating to prevent malfunctions. For human explorers, the cold of PSRs presents an even greater challenge. Spacesuits and habitats must be engineered to withstand these frigid conditions while maintaining flexibility and durability. Traditional materials often lose their elasticity in extreme cold, making it difficult for astronauts to move or manipulate tools. Life support systems must also be insulated to ensure the continuous supply of oxygen and water, both of which are prone to freezing in these conditions. Additionally, the psychological impact of working in such an unforgiving environment cannot be overlooked, as the constant threat of equipment failure or exposure adds to the mental strain of exploration. Advancements in technology have begun to address some of these challenges. Radioisotope thermoelectric generators, RTGs, which use the heat from decaying radioactive isotopes to generate electricity, have proven to be reliable heat sources for spacecraft operating in cold environments. These systems are already used in missions to distant planets and could be adapted for lunar exploration. Insulated habitats and energy-efficient heating systems are also being developed to provide safe havens for astronauts working in PSRs. Additionally, new materials with cryo-tolerant properties are being tested to withstand the rigors of such extreme cold. Using small-scale nuclear reactors to supply running power for PSR operations is a very interesting new development. These small reactors have the ability to provide enough energy to sustain dwellings, rovers, and research equipment. Additionally, research on wireless energy transfer technologies is ongoing, which might one day enable distant gadget powering without the annoyance of bulky cords. These innovations have the potential to change the game for lunar exploration by allowing us to stay in PSRs for much longer. Scientific opportunities in PSRs are as compelling as their challenges. The extreme cold preserves ancient cosmic materials such as cometary ice and interstellar dust, offering a unique window into the history of the solar system. These regions may also contain volatiles like carbon dioxide, ammonia, and methane, which could provide valuable insights into planetary formation processes. Studying the cryogenic environment of PSRs could help scientists model conditions on other icy worlds, such as Europa and Enceladus, and refine our understanding of solar system dynamics. Energy solutions for operating in PSRs are critical for future missions. Solar reflectors, strategically placed to beam light into shadowed areas, could provide localized warming and enable instruments to function. Thermal storage systems that collect and retain heat during the lunar day for use during the night are also under development. Advanced battery systems, such as lithium-sulfur or solid-state batteries, are being designed to perform efficiently in low-temperature environments. These innovations, combined with robust energy management systems, will be essential for sustaining operations in PSRs. One of the future exploration goals for PSRs is to directly sample ice deposits in order to determine their composition and origin. In order to locate untapped water and volatile resource sources, researchers are developing ground-penetrating radar and other subsurface research technologies. By establishing permanent observation stations in PSRs, we may have a greater understanding of the Moon's radiation, weather, and thermal activity. With these stations serving as testbeds for technologies aimed for far space travel, missions to further ice worlds might be made possible. There are tremendous hurdles and amazing potential in these hitherto inaccessible areas of the Moon, which are now the center of lunar exploration. What we've learnt about surviving under the Moon's icy shadow will provide the groundwork for our future exploration of the solar system. Volatiles beyond water, the Moon's hidden treasure troves. The Moon, which was formerly believed to be a desolate and lifeless rock, is turning out to contain a wealth of useful materials. The water ice in the Moon's permanently shadowed regions, PSRs, has been in the news recently due to its possible role in facilitating human space travel and colonization. But that's not all there is to it. The lunar regolith contains a wide range of volatile chemicals, each of which presents its own set of possibilities and problems for future exploration and resource extraction. These latent resources, which include elements as diverse as helium-3 and ammonia, might revolutionize the way humans interact with space in the future. Ammonia is one of the most intriguing volatiles found in PSRs. Likely deposited by ancient comet impacts, ammonia plays a crucial role in the potential development of lunar agriculture. This compound contains nitrogen, a vital element for creating fertilizers necessary to grow plants in extraterrestrial environments. Without a reliable source of nitrogen, sustaining crops on the Moon would be a formidable challenge. Ammonia's presence, therefore, offers a lifeline for future lunar colonies, enabling a degree of self-sufficiency essential for long-term habitation. Similarly, methane has been detected in these shadowed regions. Like ammonia, it may have been delivered by comets or generated through chemical reactions involving the Moon's regolith. Methane is particularly exciting for its potential as a fuel source. On Earth, it powers rockets and serves as a building block for synthetic materials. Extracting and utilizing methane on the Moon could support energy needs for habitats and machinery, reducing dependence on supplies brought from Earth. Carbon dioxide is another volatile found in the Moon's coldest regions. Trapped in the icy deposits of PSRs, carbon dioxide can be processed to produce oxygen, a critical component for breathable air and rocket propulsion. The ability to extract oxygen directly from lunar resources represents a game-changing advancement in supporting life and space travel. Moreover, carbon dioxide could play a role in industrial applications, such as manufacturing polymers and other essential materials for lunar infrastructure. Beyond these more common compounds, the Moon's PSRs might also contain sulfur dioxide and other exotic volatiles. Sulfur dioxide's potential origins lie in the Moon's ancient volcanic activity, and its discovery would provide valuable insights into the Moon's geological history. In practical terms, sulfur dioxide could be utilized to create sulfur-based building materials, aiding the construction of habitats and infrastructure on the lunar surface. These materials could offer protection against radiation and micrometeorite impacts, two significant hazards for human explorers. Helium-3, an attractive resource from the Moon, is an extremely rare isotope that has recently gained interest due to its possible use as an efficient and environmentally friendly fusion fuel. There is far less radioactive byproduct and waste from helium-3 processes compared to those using deuterium or tritium, the more conventional nuclear fusion fuels. Since it provides an almost endless supply of energy, it is very suitable for use in future fusion reactors. Although helium-3 is not present in Earth's crust in its natural abundance, the Moon's regolith has this precious isotope due to the billions of years of solar wind bombardment. However, extracting helium-3 is not without challenges. Its concentration in the lunar soil is extremely low, requiring the processing of vast amounts of regolith to obtain usable quantities. Advanced mining and separation technologies will be essential to make helium-3 extraction viable. Despite these hurdles, nations and private enterprises alike are investing in research and development, envisioning a future where the Moon serves as a global energy hub. The global interest in helium-3 underscores the growing geopolitical stakes of lunar exploration. Countries such as China and India have explicitly stated their interest in mining helium-3, while the United States and European nations are also exploring its potential. Private companies are joining the race, eyeing the lucrative opportunities presented by this unique resource. The competition for control over helium-3 deposits highlights the need for international frameworks to ensure fair and sustainable resource utilization. In situ resource utilization, ISRU, is a cornerstone of humanity's plans to establish a lasting presence on the Moon. ISRU focuses on transforming local materials into usable resources, reducing the need for costly resupply missions from Earth. Lunar volatiles, including ammonia, methane, and carbon dioxide, are central to these efforts. By converting these compounds into water, oxygen, and fuel, ISRU technologies can support life support systems, energy needs, and transportation infrastructure. Making fuel is one of the first uses for Moon volatiles. Hydrogen, an essential component of rocket propellants, may be produced by decomposing water ice, ammonia, and methane. If lunar resources could be used to produce hydrogen, the Moon may become a refueling stop for interplanetary travel, allowing trips to Mars and beyond. The logistical and economic benefits of fuel production on the Moon are enormous, and it has the ability to drastically lower the expenses of space exploration. Lunar volatiles also have implications for habitat support. Oxygen derived from water and carbon dioxide can be used to create breathable air, while nitrogen from ammonia is essential for maintaining a stable atmosphere within lunar bases. These compounds can also be combined to produce fertilizers, enabling the cultivation of crops in hydroponic or soil-based systems. Such self-sufficiency is critical for long-term missions, where resupply from Earth may not always be feasible. Advanced material development is another area where lunar volatiles could play a transformative role. Sulfur compounds, for example, could be used to create lunarcrete, a sulfur-based concrete ideal for building structures on the Moon. Unprocessed regolith itself could serve as a raw material for construction, reducing the need to transport building supplies from Earth. Glass and ceramics can also be produced from the regolith, providing additional options for creating durable and lightweight materials. Despite their immense potential, mining and extracting lunar volatiles come with significant challenges. The Moon's PSRs are among the most inhospitable environments in the solar system, with steep crater walls, unstable terrain, and temperatures plunging to -250 degrees Celsius, -418 degrees Fahrenheit. Specialized equipment capable of operating in such conditions will be essential for accessing volatile deposits. Cryogenic technologies, in particular, are needed to handle frozen volatiles without causing them to sublimate or degrade during extraction. powering mining operations in shadowed regions poses another challenge. PSRs receive little to no sunlight, necessitating alternative energy sources such as nuclear power or radioisotope thermoelectric generators, RTGs. Wireless energy transfer systems could also be employed to deliver power from sunlit areas to equipment operating in the shadows. Developing scalable and reliable energy solutions will be crucial for the success of lunar mining endeavors. A further obstacle is the transportation of harvested materials to their respective habitats or launch locations. Innovative transportation methods are needed to efficiently carry lunar volatiles, since they are commonly discovered in distant and inaccessible places. Potentially essential in this effort to lessen the dangers of human-operated transportation in dangerous areas are autonomous cars and robotic technologies. The ethical and environmental considerations of lunar resource extraction cannot be overlooked. As humanity ventures into space, it is imperative to balance scientific exploration with sustainable practices. Over-extraction of volatiles could deplete these finite resources, jeopardizing future missions and the scientific study of the Moon's unique environment. Establishing international agreements and guidelines for lunar resource management will be essential to ensure equitable access and long-term sustainability. It is also very important to keep the Moon's history intact. Sites like the Apollo landing places on the Moon symbolize historical and cultural landmarks in human achievement, making it an iconic object. In order to preserve these locations and the Moon's natural beauty, mining activities must be meticulously managed. Ensuring the preservation of unspoiled areas for the sake of scientific research is of utmost importance. These hidden gems not only hold the key to unlocking the mysteries of our solar system's past, but they also possess the power to transform our aspirations and skills. Opportunities for exploration and invention will only increase as technology advances further reveal the secrets of the Moon. Electrodynamic dangers. The Moon's charged environment. As Earth's quiet cosmic neighbor, the Moon offers an intricate and sometimes dangerous landscape for investigation. Hidden under the Moon's cratered and regolithic surface lies an invisible threat, its electrically charged atmosphere. This phenomena presents enormous difficulties for both human and robotic space operations, since the Moon does not have a magnetic field and is thus constantly exposed to the solar wind. The success of future missions depends on our ability to comprehend and reduce these electrodynamic risks as humankind prepares for increasingly ambitious lunar explorations. The Moon's environment stands out due to its lack of a protective magnetic field. Direct impact of the Sun's charged particle streams, known as solar wind, on Earth is avoided by the magnetosphere, which acts as a protective shield. But the Moon has no protective barrier. Thus, its surface is always exposed. Electric charges are created on the lunar surface as solar wind particles hit the regolith. Because of this, the Moon's electrodynamic environment is very dynamic and distinct, and this is especially true in the areas where the Moon is in shadow and along the day-night terminator. This constant bombardment leads to an intriguing phenomenon: electrostatic levitation of lunar dust. Lunar regolith, the fine layer of dust and broken rock covering the Moon's surface, becomes highly charged through interactions with the solar wind and ultraviolet radiation. When solar UV light strikes regolith particles, it ejects electrons, leaving the particles positively charged. In shadowed regions, where solar radiation does not reach, the dust may accumulate negative charges from electrons in the solar wind. These opposing charges create a delicate balance, enabling fine particles to lift and hover above the surface. This phenomenon was indirectly observed during the Apollo missions, with astronauts noting a horizon glow that scientists now attribute to levitating dust particles. While fascinating, the levitation of lunar dust poses severe risks. Lunar regolith is notorious for its abrasive nature, with sharp, jagged edges that can easily damage equipment and harm human health. The electrostatic properties of the dust exacerbate these risks, as the charged particles cling stubbornly to surfaces, including spacesuits, solar panels, and sensitive instruments. During the Apollo missions, astronauts reported that regolith clung to their visors, gloves, and tools, making cleaning an arduous task. Moreover, the abrasive particles caused wear and tear on seals and joints, jeopardizing the integrity of equipment. The hazards extend beyond adhesion. The highly charged environment can lead to electrostatic discharge, ESD, a phenomenon where accumulated electrical charges suddenly release, creating a spark. For sensitive electronics, this can be catastrophic. Rovers, landers, and other devices reliant on electronics are particularly vulnerable to ESD, which can short-circuit systems and cause mission-critical failures. Solar panels, essential for powering lunar habitats and instruments, are another weak point. Dust accumulation on panels reduces their efficiency, and static discharge can cause irreparable damage. For astronauts, the risks are equally alarming. Spacesuits designed to protect against extreme temperatures and radiation could become a medium for electrostatic shocks. The static buildup might cause sudden discharges when astronauts touch conductive surfaces, potentially endangering their safety. The challenges posed by this charged environment are further compounded by the unique conditions of the Moon's surface. The electrostatic properties of regolith vary depending on location, solar activity, and the time of day. In the shadowed regions, particularly the permanently shadowed craters near the poles, the lack of sunlight leads to extreme charge imbalances. These areas, already treacherous due to their frigid temperatures and uneven terrain, become even more perilous under the influence of electrostatic forces. The fine dust particles, suspended by levitation or carried by static forces, can interfere with navigation and obscure visibility, creating additional obstacles for exploration. Despite these dangers, humanity's determination to explore and utilize the Moon has spurred innovative solutions to mitigate the risks associated with its charged environment. Advances in material science have led to the development of conductive or anti-static materials for spacesuits and equipment. These materials are designed to prevent the buildup of electrical charges, reducing the likelihood of static shocks and ESD. Spacesuits made with such materials could safeguard astronauts against electrodynamic hazards, ensuring their safety during extended missions. The Electrodynamic Dust Shield, EDS, is another intriguing innovation that employs alternating electric fields to deflect dust particles away from surfaces. Using this invention, solar panels, visors, and other equipment might remain clean and functioning, even in situations with a lot of dust. To counteract static electricity on regolith and adjacent surfaces, researchers are also investigating active charging devices. These systems try to keep the electrical balance under control so that dust doesn't stick and static electricity doesn't happen. Robotic technologies also play a crucial role in navigating the Moon's electrodynamic environment. Rovers equipped with advanced sensors and autonomous navigation systems can traverse dusty and uneven terrain with minimal human intervention. These machines can perform tasks like dust removal, material transport, and environmental monitoring, reducing the need for astronauts to operate in hazardous conditions. Furthermore, robotic cleaning systems are being designed to maintain the cleanliness of habitats and equipment, ensuring that dust does not compromise mission integrity. Innovations in habitat design are equally important. Lunar habitats must incorporate grounding systems to dissipate electrical charges safely. Insulated entry points can prevent static shocks when astronauts re-enter habitats. Advanced filtration systems are being developed to capture and neutralize airborne dust particles, preventing them from contaminating living spaces. Dust-resistant coatings on exposed surfaces further enhance the durability of habitats and vehicles, ensuring they remain operational despite prolonged exposure to the Moon's harsh environment. The scientific community is also investing in research to better understand the Moon's electrodynamic environment. Detailed studies of charge dynamics, conducted through simulations and lunar analog environments on Earth, are shedding light on the behavior of charged regolith under various conditions. Collaborative efforts between space agencies and private companies are driving the development of scalable solutions for electrostatic hazards, ensuring that future missions are better equipped to navigate the challenges. These breakthroughs have far-reaching ramifications that go beyond only the Moon. Mars, asteroids, and Mercury are all airless entities that might benefit from the lessons learned about controlling electrodynamic hazards on the Moon's surface. Any number of settings, from dusty deserts on Earth to the surfaces of other planets, might benefit from the technology created to reduce electrostatic risks. Nevertheless, significant challenges remain. The Moon's charged environment is dynamic and influenced by solar activity, necessitating continuous monitoring and adaptation. Solar storms and flares, unpredictable by nature, can exacerbate charge imbalances and increase the risks of static discharge. Developing robust systems that can withstand these variations is critical for the success of long-term lunar missions. Illuminating the unknown, ShadowCam and the future of lunar exploration. Axial tilt represents both a challenge and an opportunity for lunar exploration. Advances in imaging technology, particularly tools like ShadowCam and other high-sensitivity instruments, are reshaping our ability to study these enigmatic landscapes. This transformative leap in imaging has begun to uncover the mysteries within the Moon's darkest craters, paving the way for groundbreaking discoveries and future missions. At the forefront of this revolution is ShadowCam, a state-of-the-art imaging tool developed to reveal what lies hidden in the Moon's most shadowed corners. Unlike conventional cameras, ShadowCam is 200 times more sensitive than its predecessor, the Lunar Reconnaissance Orbiter Camera, LROC. This heightened sensitivity allows it to capture faint reflections of light bouncing off nearby lunar terrain, enabling detailed imaging even in regions where sunlight has not penetrated for billions of years. ShadowCam represents a technological milestone, opening a window into areas previously thought inaccessible. Complementing ShadowCam are a suite of other imaging instruments, such as infrared spectrometers, thermal cameras, and synthetic aperture radar, SR. These technologies work in concert, offering different perspectives and data on the Moon's surface and subsurface. For example, SAR can penetrate the regolith to reveal subsurface structures, while thermal imaging identifies areas of extreme cold and potential volatile deposits. Together, these tools provide a comprehensive picture of PSRs, enhancing our understanding of their geology, composition, and potential resources. The methodology behind these imaging advancements is equally impressive. ShadowCam amplifies faint light sources, such as earthshine, the light reflected from Earth to the Moon, and sunlight scattered off adjacent terrain. This capability is bolstered by sophisticated algorithms that process raw data into clear, high-resolution images. Additionally, multispectral imaging techniques enable scientists to differentiate between materials based on their spectral signatures, helping to identify water ice, hydroxyl, and other compounds within the PSRs. These advancements are not merely technical feats, they are revolutionizing our understanding of PSRs. Detailed mapping of crater interiors, a task once considered impossible, is now a reality. ShadowCam's high-resolution images have revealed intricate geological formations, including boulders, ridges, and even faint tracks left by ancient lunar activity. Such discoveries provide critical insights into the Moon's geological history, offering clues about its formation and evolution. New information on the distribution of lunar ice is really interesting. Locations with high reflectivity have been seen by ShadowCam and similar instruments, suggesting the possibility of ice deposits. For future missions, this data is priceless, since it shows where volatiles like water ice may be collected for in-situ resource utilization, ISRU. In addition, the capacity to catalog these assets lends credence to the goal of creating long-term lunar settlements that can cut back on Earth-based resource use. ShadowCam's contributions extend beyond individual discoveries. It represents a collaborative effort between NASA and South Korea's Danuri mission, demonstrating the power of international partnerships in advancing space exploration. The Korea Pathfinder Lunar Orbiter, KPLO, or Danuri, carries ShadowCam alongside its suite of scientific instruments. Together, they have delivered unprecedented insights into the Moon's shadowed regions, including the famed Shackleton crater. ShadowCam's detailed images of Shackleton's interior have revealed boulder trails and other features that suggest dynamic geological processes at work. Similarly, the Lunar Reconnaissance Orbiter, LRO, has played a pivotal role in expanding our knowledge of PSRs. By combining ShadowCam's images with LRO's thermal and spectroscopic data, scientists have identified areas of interest that extend beyond water ice. For example, potential deposits of methane, ammonia, and other volatiles have been detected, hinting at the complex chemistry occurring within these regions. Such findings underscore the importance of integrating multiple data sources to unravel the mysteries of PSRs. Despite these achievements, imaging alone has its limitations. While ShadowCam provides an unparalleled view of surface features, it cannot directly detect buried volatiles. Subsurface analysis relies on complementary methods, such as radar and spectroscopy, to confirm the presence of hidden resources. Moreover, the high reflectivity observed in some areas may result from non-volatile materials, such as silica or metallic oxides, complicating interpretations. This ambiguity highlights the need for ground-based sampling missions to validate orbital findings. The fact that PSRs are not easily accessible is another obstacle. Imaging can capture the appearance of characteristics, but it can't capture how these areas are constantly changing. Dust from the Moon, carried by micrometeorites or electrostatic forces, can change the distribution of volatiles and obscure surface features as it moves over the Moon over time. Continuous monitoring and adaptive technology are necessary due to the complexity that this dynamic environment adds to imaging attempts. The implications of advanced imaging extend far beyond scientific curiosity. ShadowCam and similar instruments are instrumental in enhancing future mission planning. By providing detailed maps of PSRs, these tools enable the selection of safe landing sites and navigation paths for rovers and landers. Such data minimizes risks and maximizes the efficiency of exploration missions, ensuring that resources and efforts are directed toward areas of greatest scientific and practical value. Moreover, imaging technology supports ISRU by identifying promising regions for resource extraction. Locating deposits of water ice, helium-3, and other materials is critical for establishing self-sustaining lunar habitats. Imaging data not only guides the extraction process, but also informs the design of infrastructure and systems needed to utilize these resources effectively. With the return of men to the Moon in sight, imagery will play an increasingly crucial role in directing future human exploration. In order to create fast and safe routes and to identify any dangers, detailed maps of PSRs are quite helpful. To maximize the safety and success of lunar excursions, mission planners must have a good grasp of the topography and the distribution of resources in order to optimize the placement of shelters and equipment. The broader impact of advanced imaging technology extends to planetary exploration beyond the Moon. The techniques refined through ShadowCam and similar instruments are directly applicable to missions targeting Mars, Europa, and other celestial bodies. These advancements pave the way for a new era of exploration, where imaging serves as a cornerstone for scientific discovery and human expansion into the cosmos. Further in-depth information will be provided by integrating ShadowCam with future missions such as Artemis. We will get a deeper knowledge of the Moon and its shadowed areas as multispectral analysis, processing methods, and resolution continue to increase, opening up new possibilities. Our capacity to investigate the Moon's permanently shadowed regions has been greatly enhanced by the advent of ShadowCam and other cutting-edge imaging technology. These techniques are transforming lunar exploration in a variety of ways, including precise mapping, resource identification, mission planning, and ISRU. Chandrayaan-3 and the global quest to uncover lunar secrets. Chandrayaan-3, India's third lunar mission, made groundbreaking strides in unraveling the mysteries of the Moon's south pole, an area that has captured global attention for its potential to host vital resources and reveal the Moon's geological history. While the mission celebrated several firsts, it also raised new questions that challenge our understanding of the Moon and its resources. With the launch of Chandrayaan-3, India's space exploration capabilities took a giant leap forward. The Vikram lander and the Pragyan rover, which were intended to conduct on the Moon experiments, were the main components of it. Their research provided priceless information about the lunar regolith's chemical makeup close to the South Pole. Element detection by Pragyan was accomplished by the use of state-of-the-art instruments such as the alpha particle X-ray spectrometer, APXS, laser-induced breakdown spectroscopy, LIBS, and sulfur. These findings increased our comprehension of the Moon's tectonic history, with sulfur offering crucial proof of long-gone volcanic eruptions and their consequences for the surface's development. Despite these triumphs, one notable absence stood out: the detection of hydrogen, a key indicator of water ice. This lack of evidence contradicted earlier findings from missions like Chandrayaan-1 and NASA's L-Cross, which suggested substantial hydrogen deposits in the permanently shadowed regions, PSRs, of the lunar poles. The absence of direct water ice signatures raised questions about its distribution, the challenges of detection, and whether previous evidence could have been misinterpreted. This discrepancy underscores the need for more advanced tools capable of probing deeper into the subsurface, where water ice might be trapped. The Vikram lander's temperature readings added another layer of intrigue to Chandrayaan-3's discoveries. By measuring surface and subsurface temperatures, Vikram revealed a striking thermal gradient. While the surface temperature reached a sweltering 60 degrees Celsius, just 8 centimeters below the surface, it dropped to a frigid -10 degrees Celsius. This finding confirmed that lunar regolith is a poor heat conductor, making it a natural insulator. These insights are vital for planning future lunar habitats, as they highlight the challenges of maintaining stable temperatures in a harsh environment. Vikram's seismic readings also contributed to our understanding of the Moon's interior. The detection of potential moonquakes provided clues about the Moon's subsurface activity, including tectonic movements and the structural integrity of its crust. Such data are essential for designing infrastructure that can withstand the unique conditions of the lunar environment. Vikram's contribution extended beyond static measurements. Its successful hop maneuver, where it briefly lifted off and repositioned itself, demonstrated the potential for future landers to navigate and explore more challenging terrains. While Chandrayaan-3's findings were monumental, they were not without limitations. Pragyan's exploration was restricted to a radius of approximately 100 meters from the lander, due to its design and manual navigation from Earth. Despite these constraints, the rover managed to navigate around hazardous craters and avoid potential accidents, showcasing the precision and adaptability of its engineering. However, its limited range emphasized the need for more autonomous rovers with extended operational capabilities to explore vast and diverse terrains. Future missions will be greatly impacted by the discoveries from Chandrayaan-3. For example, the Artemis program at NASA seeks to create a long-term human settlement on the Moon by optimizing the use of existing resources and building new habitats. The findings made by Chandrayaan-3 will be expanded upon by the Artemis missions, which will use more advanced instruments to further improve the mapping of lunar volatiles. Similarly, the Chang'e program in China has accomplished a lot in the realm of lunar research. The South Pole will be the focus of the next Chang'e 6 and Chang'e 7 missions, which aim to further our knowledge of PSRs and the resources they may contain. Korea's Danuri mission, featuring the advanced ShadowCam instrument, complements Chandrayaan-3's efforts by providing high-resolution images of PSRs. ShadowCam's sensitivity allows it to peer into the darkest corners of the Moon, revealing surface features and potential volatile-rich areas that other instruments might miss. These complementary datasets from international missions are vital for creating a comprehensive understanding of the Moon's resources and environmental conditions. Chandrayaan-3 identifies the need to reconcile its findings with prior evidence as one of the major problems. Despite previous missions' findings of large water ice deposits in PSRs, Chandrayaan-1 and L-Cross, in situ measurements conducted by Chandrayaan-3 did not detect any direct evidence of hydrogen. This disparity highlights the necessity for cross-validation of results and the intricacy of lunar research. It further emphasizes the shortcomings of existing technology in identifying and measuring volatile substances under the Earth's surface. The implications of Chandrayaan-3's discoveries extend beyond science. For lunar base planning, its findings will help refine the selection of sites for resource extraction and habitat construction. The detection of sulfur and other volatiles opens possibilities for in situ resource utilization, from building materials to chemical processes that support life and fuel production. These resources could be pivotal in establishing a self-sustaining lunar colony and reducing dependence on Earth for supplies. Technological advancements inspired by Chandrayaan-3 are already shaping the design of future missions. The mission's low-cost, high-impact approach demonstrated the feasibility of achieving significant scientific milestones with constrained budgets. This model could encourage other nations and private entities to invest in lunar exploration, fostering a more collaborative and competitive environment. The findings also underscore the need for subsurface exploration. While surface measurements provide valuable data, they fall short of revealing the hidden layers where critical resources like water ice may reside. Future missions, equipped with drilling technologies and advanced imaging tools, will be essential to uncover these buried treasures and solve the mystery of lunar volatiles. The accomplishment of Chandrayaan-3 is a watershed moment in global cooperation, and it goes beyond the obvious scientific and technological benefits. Cooperative exploration of the Moon can be facilitated by shared datasets and combined expeditions, which enhance our understanding of lunar science on a global scale. The ever-changing character of lunar exploration is exemplified by Chandrayaan-3's significant accomplishments and the issues it posed. Although it revealed new information on the Moon's makeup and atmosphere, it also highlighted our present knowledge gaps and the technical challenges that still need to be overcome. Survival strategies: building lunar bases in the Moon's harshest regions. These frigid conditions require advanced insulation and robust heating systems to protect both astronauts and equipment. Unlike on Earth, where a magnetic field shields us from harmful radiation, the Moon offers no such protection. Cosmic rays and solar radiation bombard its surface, making radiation shielding a critical aspect of any lunar base. This vulnerability also necessitates innovations like using regolith as a natural shield, water tanks in walls to absorb radiation, or even electromagnetic fields to deflect harmful particles. Adding to the difficulty is the omnipresent lunar regolith, a fine abrasive dust that can cause significant wear and tear on machinery and pose health risks to humans. Lunar regolith is electrostatically charged due to solar-wind interactions, making it stick to surfaces, including spacesuits and equipment. This sharp-edged dust can penetrate seals, damage instruments, and irritate respiratory systems. Engineers are already developing solutions such as dust-resistant coatings, electrodynamic dust shields, and even liquid nitrogen systems to mitigate the effects of regolith. Ensuring safety while navigating regolith-laden terrain is one of the most pressing engineering challenges for lunar bases. The extreme cold and darkness of PSRs also present significant energy challenges. Solar power, a reliable energy source in sunlit areas, is not viable in these shadowed regions. Instead, nuclear power plants or large-scale energy storage systems are proposed to meet energy demands. Compact nuclear reactors could provide a continuous power supply, while advanced battery systems or thermal storage could store energy for use during prolonged periods of darkness. Another innovative idea involves beaming energy from sunlight-rich areas to bases in PSRs via wireless power transmission. Insights from Earth's polar research stations have proven invaluable in addressing these challenges. Facilities in Antarctica, where temperatures plunge to similarly extreme levels, have pioneered cold weather engineering techniques. Durable insulation materials, effective heating systems, and renewable energy solutions like wind turbines adapted for cold climates offer a foundation for designing lunar habitats. Additionally, the psychological resilience strategies developed for isolated and extreme environments on Earth will be crucial for maintaining the mental health of lunar settlers. When it comes to constructing habitats on the Moon, technologies like lunarcrete provide groundbreaking possibilities. Lunarcrete, a building material derived from regolith, could eliminate the need to transport large amounts of construction materials from Earth. Inflatable modules and hybrid designs that combine lightweight Earth-sent structures with on-site materials offer practical solutions for rapid base deployment. Advanced insulation materials that withstand extreme temperatures and abrasive dust will be vital for these habitats. Using 3D printing technologies, autonomous robots could fabricate structures directly on the Moon, reducing the risk and cost of human labor in dangerous conditions. Radiation shielding is another critical factor in habitat design. Layering regolith over habitats provides effective protection against cosmic rays and solar radiation. Water, a versatile resource, can double as a radiation shield when stored in tanks embedded in the walls of habitats. Some researchers are even exploring the concept of artificial magnetic fields to mimic Earth's protective magnetosphere, although this remains a long-term goal. Energy systems are central to survival and sustainability. Nuclear power is an appealing solution, offering a consistent energy supply in regions without sunlight. These reactors, specifically designed for space missions, are compact, safe, and capable of running for years without refueling. Energy storage systems, such as high-capacity batteries or thermal storage, could complement nuclear power by storing excess energy during operational peaks. Wireless power transmission, where energy collected in sunlit areas is sent to shadowed bases, presents a futuristic but promising alternative. Life support systems are equally vital for lunar bases. Closed-loop systems for recycling air and water can ensure sustainability in a resource-scarce environment. Technologies that extract oxygen from regolith or water ice can supplement air supplies, while hydroponic and aeroponic systems can grow food using minimal water and soil. Such innovations could make a lunar base self-sufficient, reducing reliance on resupply missions from Earth. The role of 3D printing and automation in lunar base construction cannot be overstated. Robotic systems capable of 3D printing habitats and infrastructure using regolith are already being tested. These autonomous machines can work in extreme conditions without risking human lives. Additive manufacturing, or 3D printing, can also produce tools, spare parts, and even components for energy systems on demand, reducing the need for bulky shipments from Earth. AI systems integrated into these operations could optimize resource management, construction schedules, and energy distribution. Recycling will play a pivotal role in sustaining a lunar colony. In situ resource utilization, ISRU, focuses on extracting oxygen, hydrogen, and metals from lunar materials. Oxygen and hydrogen can be used for life support and fuel, while metals like aluminum and titanium can support construction and manufacturing. Waste recycling will ensure that biological and non-biological materials are repurposed effectively, further reducing dependency on Earth. One of the most important parts of survival tactics is creating a living space that makes people feel good. Regardless of how harsh the weather outside is, thermal regulation systems will keep you comfortable by controlling the temperature inside. To mitigate the negative impacts of low gravity on human health, artificial gravity solutions like centrifuge-like devices or spinning modules might be implemented. Astronauts might still take in the sights and light from the outside world, with the help of radiation-proof windows constructed from transparent shielding materials. Mobility and transport solutions are also necessary for navigating the Moon's harsh terrain. Lunar rovers equipped with advanced navigation systems and dust-resistant designs can transport materials and personnel across uneven surfaces. Underground tunnels, potentially located within natural lava tubes, offer shelter from radiation and extreme temperatures while connecting base modules. Landing pads constructed from regolith-based materials could prevent dust clouds during spacecraft arrivals and departures. Long-term sustainability hinges on creating closed ecosystems and integrating lunar infrastructure with orbital assets. Biospheres capable of sustaining human life independently could serve as models for future space habitats. Redundant systems for power and life support will provide critical backups in emergencies. Lunar orbit stations could act as relay hubs for resources and personnel, enhancing logistical efficiency. The establishment of a lunar outpost is not without its ethical implications. To keep the Moon in its pristine form, resource exploitation must have little environmental effect. In order to keep disputes over territory and resources at bay, international cooperation is crucial. The equitable and long-term utilization of lunar resources necessitates the establishment of regulatory structures. Research opportunities abound for lunar bases. These facilities can serve as platforms for long-term lunar and astronomical studies, human physiology research, and technology testing for deep space missions. Understanding the Moon's unique environment will provide insights that are invaluable for future exploration of Mars and beyond. The construction of a lunar base under the harsh conditions of the Moon's planetary surface regions, PSRs, is an enormous task for humanity. We may, however, triumph over these challenges by embracing new technology, learning from Earth, and working together. Using innovative building techniques in conjunction with locally sourced materials, we can mitigate the risks of radiation, freezing temperatures, and lunar dust. Innovations in lunar power systems, illuminating the path to exploration and survival. Obtaining enough energy is crucial for any lunar exploration mission. Nevertheless, state-of-the-art solutions are required to overcome the obstacles of producing, storing, and distributing electricity in the hostile lunar environment, especially in the persistently shadowed regions, PSRs. Even the most daring lunar missions run the danger of failing due to unreliable power systems. Overcoming these challenges will need innovation and technology if we are to embark on prolonged exploration and, eventually, colonization. Solar power, the cornerstone of terrestrial renewable energy, faces severe limitations on the Moon. While abundant sunlight bathes the equatorial regions during the long lunar day, PSRs, by definition, remain shrouded in darkness for billions of years. Even where sunlight is available, the Moon's 2-week-long day-night cycle creates significant challenges for solar-powered systems. During the lunar night, temperatures plummet and solar panels lie dormant, necessitating the development of robust energy storage solutions. To address these challenges, scientists and engineers are exploring innovative ways to harness solar energy in shadowed regions. One approach involves placing solar panels on elevated structures or nearby sunlit peaks, such as crater rims, to capture light continuously. This energy can then be transmitted wirelessly to habitats or rovers within PSRs using laser or microwave beams. Wireless power transfer systems eliminate the need for cumbersome cables and offer flexibility in powering mobile units. Despite these advancements, solar power alone may not suffice for missions in PSRs or during extended lunar nights. Nuclear power emerges as a promising alternative, offering reliable, uninterrupted energy. Small modular reactors, SMRs, and radioisotope thermoelectric generators, RTGs, are at the forefront of this effort. SMRs, compact and efficient, can provide substantial power outputs for habitats and larger operations. RTGs, which convert the heat from radioactive decay into electricity, are well suited for powering rovers and instruments. NASA and other space agencies are actively pursuing nuclear power solutions. The Kilopower project, for example, aims to develop a compact nuclear fission reactor capable of generating 10 kilowatts of power, enough to sustain multiple lunar habitats. These reactors are designed to operate autonomously with minimal maintenance, making them ideal for long-duration missions. Their ability to function in extreme cold and darkness makes them invaluable for exploring and colonizing PSRs. Wireless power transfer is another critical innovation, enabling energy distribution on the Moon. By using directed energy beams, such as microwaves or lasers, power can be transmitted over long distances to rovers, instruments, or habitats in shadowed regions. This technology minimizes the need for physical connections, reducing the risk of damage from lunar dust or terrain. Additionally, wireless power systems can support the mobility of autonomous rovers, enabling them to explore PSRs without returning to a base station for recharging. Missions to the Moon also rely heavily on energy storage. In order to store energy effectively and endure the severe conditions of the Moon, scientists are developing advanced fuel cells and batteries. Although lithium-ion batteries are popular, they can't withstand really low temperatures. Scientists are looking into different options, such solid-state batteries, which have more energy density and are more durable. Another potential option for long-term energy storage is fuel cells, which produce electricity via chemical processes. Energy storage systems must also support redundancy to ensure mission reliability. Hybrid systems combining solar, nuclear, and battery technologies can provide uninterrupted power by leveraging the strengths of each approach. For instance, solar power can charge batteries during the lunar day, while nuclear reactors supply continuous energy during the night or in shadowed regions. This redundancy is crucial for maintaining life support systems, powering scientific instruments, and ensuring the safety of astronauts. The importance of energy extends beyond survival to enabling exploration and scientific discovery. Powering advanced instruments, rovers, and habitats allows scientists to study the Moon's geology, search for water and volatiles, and conduct experiments. Reliable energy systems also support communication with Earth, data transmission, and navigation, all of which are critical for mission success. Innovations in energy systems are not limited to large-scale operations. Portable power solutions, such as compact fuel cells and modular battery packs, are essential for mobile exploration. These systems enable astronauts and robotic explorers to venture into PSRs and other remote areas without being tethered to a central power source. Portable power units can also support emergency operations, providing backup energy in the event of a system failure. The integration of artificial intelligence, AI, and autonomous systems further enhances the efficiency of lunar power systems. AI can optimize energy usage, monitor system performance, and predict maintenance needs, reducing downtime and increasing operational efficiency. Autonomous systems can also manage power distribution, ensuring that critical functions receive priority during peak demand. Improving lunar power technology relies heavily on international cooperation and business sector engagement. Companies, universities, and space agencies are collaborating on new energy options. Solar and nuclear power systems for the Moon, for instance, have been developed and deployed by private enterprises in conjunction with NASA's Artemis program. Working together, we can cut expenses and speed up technical advancement, opening up lunar exploration to more people. There will be more general uses for the knowledge gained from studying lunar power systems. Mars and other planetary planets with comparable energy difficulties can benefit from innovations created for the Moon. Additionally, they have the potential to motivate improvements in Earth's energy systems, which would enhance resilience and sustainability. Building dependable and efficient power systems is essential for exploring and colonizing the Moon. It will need innovation, teamwork, and state-of-the-art technology to overcome the obstacles of energy generation, storage, and distribution on the Moon. Sustaining life on the Moon. Lunar farming and bioregenerative life support. The fundamental difficulty of lunar farming stems from the fact that lunar circumstances are fundamentally different from Earth's. Moon features jagged, nutrient-poor regolith for a surface, no atmosphere to shield from radiation and meteoroids, and wildly fluctuating temperatures. Notwithstanding these obstacles, encouraging results have been observed in Earth-based plant growth tests using lunar regolith mimics. Scientists have proven that, with the right fertilizers, lunar soil can sustain plant life by growing potatoes, radishes, and lettuce. To make regolith a more workable agricultural substrate, organic materials, microorganisms, or even synthetic nutrients can be added to increase its fertility. Water is another critical component of lunar farming, and its scarcity on the Moon poses significant obstacles. The discovery of water ice in permanently shadowed regions, PSRs, has opened new possibilities for irrigation and other agricultural needs. Extracting this water and purifying it for use in controlled farming environments will require innovative technologies. Additionally, recycling water within a closed-loop system will be essential to minimize waste and ensure a sustainable supply for both human consumption and agriculture. Beyond water, other volatiles present in PSRs, such as ammonia and carbon dioxide, play vital roles in supporting plant growth. Ammonia can be used as a nitrogen source for fertilizing crops, while carbon dioxide is crucial for photosynthesis. These resources, combined with advanced agricultural techniques, could enable the production of food on the Moon without relying heavily on resupply missions from Earth. Creating controlled environments for farming on the Moon is a complex engineering challenge. Greenhouses must be sealed and pressurized to protect plants from the vacuum of space, while also shielding them from harmful radiation. Artificial lighting systems will need to mimic Earth-like conditions to optimize photosynthesis, and temperature control will be critical to counteract the Moon's extreme day-night cycles. These systems will not only support plant growth, but also serve as havens of stability and comfort for human settlers. The creation of integrated food production and water and air recycling systems is essential to lunar farming. The plants in these ecosystems not only feed the people who live there, but they also absorb the carbon dioxide that people breathe and produce oxygen. By decomposing trash and reintroducing nutrients to the environment, systems of microbes and algae can supplement plant-based life support. If lunar missions are to remain viable in the long run, these closed-loop technologies are essential for lowering their reliance on Earth's resources. Reducing the need for constant resupply from Earth is one of the primary advantages of in-situ food production. Transporting supplies to the Moon is costly and logistically challenging, making local food production a more economical and sustainable solution. By cultivating crops on the Moon, settlers can significantly reduce their reliance on Earth and establish a self-sufficient presence in space. Biotechnology and synthetic biology are also playing crucial roles in advancing lunar farming. Genetically modified plants designed to thrive in low-gravity, high-radiation environments could revolutionize space agriculture. Researchers are exploring the potential of extremophile organisms, microbes and plants that naturally survive in harsh conditions to enhance the resilience of lunar farming systems. Synthetic biology approaches, such as engineering nutrient-dense crops with faster growth rates, further expand the possibilities for sustainable food production. Hydroponics and aeroponics provide an alternative to conventional soil-based farming for growing plants in space. The difference between hydroponics and aeroponics is that the former employs nutrient-rich water to grow plants, while the latter uses a mist or air to reach the roots directly. Because they use less water and don't require soil, these approaches are very efficient. Their adaptability to the Moon's limited resources makes them a promising candidate for use in lunar farming systems. Microbial and fungal systems also have significant potential to support lunar farming. Beneficial microbes can help break down lunar regolith, releasing nutrients that plants can absorb. Fungi, known for their decomposing abilities, can recycle organic waste into usable nutrients, creating a sustainable cycle of growth and renewal. Additionally, fungi-based materials may serve as substitutes for soil, or even as structural components in farming systems. Scaling lunar agriculture to support larger populations presents additional challenges. While small-scale systems are sufficient for initial missions, long-term colonization will require larger operations capable of feeding hundreds or even thousands of people. This necessitates optimizing resource efficiency, managing risks of crop failures, and developing strategies to balance automation with human oversight. Ensuring that lunar farming meets the nutritional needs of settlers is another critical consideration. A diverse crop selection, including protein-rich plants like soybeans and lentils, will be essential for maintaining a balanced diet. Researchers are also exploring lab-grown meat and algae as supplemental food sources, providing additional protein and essential nutrients. Fortifying crops with vitamins and minerals could further help prevent nutritional deficiencies among lunar inhabitants. Energy requirements for lunar farming are substantial, particularly for maintaining temperature stability, lighting, and water recycling in greenhouses. Advanced power systems, such as nuclear reactors and solar energy solutions, will be crucial for sustaining agricultural operations. Energy storage technologies, including batteries and fuel cells, will ensure a reliable power supply during lunar nights when solar energy is unavailable. Lunar farming innovations have implications far beyond the Moon. The techniques and technologies developed for space agriculture can address challenges on Earth, such as farming in extreme environments like deserts or polar regions. Water recycling, resource conservation, and resilient crop systems could revolutionize sustainable agriculture and food security on our planet. The psychological benefits of farming in space should not be underestimated. Caring for plants provides a sense of purpose and connection to life, which is particularly valuable in isolated and hostile environments. Greenhouses can serve as sanctuaries for relaxation and emotional well-being, helping astronauts cope with the mental challenges of living on the Moon. Moon farming has great potential, but there are still many obstacles to overcome. There is a grave danger to human existence if closed-loop systems fail, and there is a lack of food or oxygen. Risks to agricultural activities might arise from contamination with pathogenic microorganisms or fungus. To tackle these risks, it is crucial to have systems that are dependable and redundant, as well as strong mitigation techniques. The advancement of lunar farming will be greatly influenced by future research and development. Important first steps include learning about the lunar regolith's chemical composition, putting farming systems through their paces in Earth's lunar-like conditions, and encouraging partnerships between space organizations and agricultural researchers. A viable space colony can be established by incorporating farming into larger lunar colonization initiatives. The world will be forever changed if moon farming takes off. As a springboard for future human exploration of Mars and beyond, it has the potential to bring poor nations together in space agriculture, offer up new opportunities, and encourage international collaboration. The mystery of lunar water cycles, a dynamic resource in an unlikely place. For a long time, people assumed that the Moon was a barren wasteland, without any of the green, watery elements that make Earth unique. On the other hand, recent investigations have shown that the Moon does in fact hold water, albeit in minute quantities, and even displays a water cycle. The consequences of this finding for research, exploration, and the possibility of colonizing our galactic neighbor are immense. The mysteries of the lunar water cycle can be unraveled by investigating its mechanisms, evidence, and obstacles. Over the years, data from missions like NASA's Lunar Reconnaissance Orbiter, LRO, and the Stratospheric Observatory for Infrared Astronomy, SOFIA, have painted a surprising picture. These observations suggest that water is not confined to the Moon's permanently shadowed regions, PSRs, but may exist as trace molecules across the entire surface. As temperatures rise during the lunar day, water appears to dissipate into the thin exosphere, only to settle back onto cooler surfaces as night falls. This cyclical behavior hints at a complex, dynamic process, that challenges our understanding of the Moon as a static, lifeless body. The LRO found spectrum evidence that pointed to hydroxyl, oak, and water, H2O molecules, which was one of the biggest surprises. The tremendous temperature swings between the sweltering daytime temperatures and the bone-chilling nighttime lows appear to propel these molecules across the lunar surface. Similar to a tenuous water cycle, but quite different from the hydrological processes on Earth, is the phenomena that has been seen. On such a hostile surface, how could these molecules of water even exist? Solar wind, the stream of charged particles emitted by the Sun, plays a pivotal role in the Moon's water chemistry. Hydrogen ions from the solar wind bombard the lunar regolith, reacting with oxygen-bearing minerals to form hydroxyl. In some cases, these reactions may further lead to the creation of water molecules. Another contributing factor is the continuous bombardment of micrometeorites. These tiny, high-velocity projectiles release energy upon impact, melting the regolith momentarily and potentially combining hydroxyl into water. While solar wind and micrometeorites explain part of the story, they do not fully account for the observed water dynamics. The sublimation of ice from permanently shadowed craters is another proposed mechanism. During brief periods of sunlight exposure, some water ice may vaporize and migrate to cooler regions, only to refreeze when temperatures drop. This interplay between sublimation and condensation creates a fragile balance that sustains the lunar water cycle. Understanding the Moon's water distribution presents a significant challenge. Observations reveal inconsistencies, with water appearing more abundant in some regions than others. This uneven distribution raises questions about the underlying processes that govern water movement. Is the observed water native to the Moon, or is it continuously replenished by external sources like comets and asteroids? The answer lies in understanding the origins of lunar water. A theory puts the Moon's water content attributable to encounters with comets and asteroids a billion years ago. These frozen moons and other space rocks deposited vast amounts of water, some of which settled as regolith or became stuck in shadowed craters. One alternative explanation is that water vapor was discharged into the atmosphere by the Moon's early volcanic eruptions, which then condensed and solidified in the Moon's cooler areas. Neither of these explanations is completely satisfactory, but they do account for the fact that water persists in sunny places. A critical factor in sustaining the lunar water cycle is the regolith itself. This fine, powdery layer of rock fragments covers the Moon's surface and interacts dynamically with water molecules. Regolith can trap water in tiny bead-like structures formed during micrometeorite impacts. These beads may act as temporary reservoirs, releasing water under specific conditions. However, the exact mechanisms of this trapping and release process remain poorly understood. The sustainability of the lunar water cycle is another pressing question. The Moon's low gravity means that water molecules can easily escape into space, especially when exposed to solar radiation. Despite this, the cycle persists, suggesting a delicate equilibrium. Researchers are keen to determine whether this balance represents a finite resource or a renewable one, continuously replenished by external and internal processes. The lunar water cycle remains a mystery, and only technological progress can reveal its secrets. The data on water distribution and flow has been invaluable thanks to the instruments aboard the LRO, such as heat sensors and spectrometers. To a similar extent, Sophia's aerial observations have found water molecules in sunny areas, casting doubt on the idea that water is limited to craters under darkness. More sensitive devices on board future flights might monitor water movement in real time, shedding light on this mysterious phenomena. The implications of the lunar water cycle extend beyond scientific curiosity. For future lunar colonies, water is a vital resource, essential for drinking, agriculture, and oxygen production. Understanding how water moves across the lunar surface can inform strategies for harvesting and utilizing this resource. For instance, knowing where water is most likely to accumulate during the lunar night could guide the placement of extraction facilities. Complexity is further increased by the fact that water and PSRs interact with one another. Because they have been out of the sun's rays for billions of years, these icy areas naturally retain water molecules as they migrate. The severe weather and poor visibility make it an uphill battle to monitor the flow of water into and out of PSRs. To fully understand these interactions and tap into PSR's water reservoir potential, cutting-edge imaging and in-situ measurements are required. The broader implications of the lunar water cycle extend to other celestial bodies. By studying the Moon, scientists gain insights into the behavior of volatiles on airless worlds like Mercury and asteroids. These findings could inform our understanding of ancient water cycles on Mars and the potential for water in exoplanetary systems. The Moon thus serves as a natural laboratory for exploring the dynamics of water in extreme environments. The exact mechanisms driving the lunar water cycle, its origins, and its sustainability are still subjects of debate. The lack of in-situ data from key regions further complicates the picture. To address these gaps, researchers are calling for missions specifically designed to observe water movement on the Moon's surface. These missions could deploy rovers equipped with advanced spectrometers to analyze water interactions with regolith in real time. Astronauts on future Moon missions could play a crucial role in collecting samples, testing water extraction methods, and observing the cycle firsthand. However, human activities also pose risks, potentially disrupting the natural balance of the water cycle. Careful planning and sustainable practices will be essential to minimize our impact on this delicate system. Finding the lunar water cycle changed our perception of the Moon from a lifeless, desolate wasteland to a living, breathing planet. The scientific community's horizons have been expanded by this new information, which has real-world implications for space travel and colonization. The future of lunar exploration: collaborations, innovations, and challenges. Ahead, NASA's Artemis program is at the forefront of modern lunar exploration. Named after the twin sister of Apollo, Artemis seeks to establish a sustainable human presence on the Moon. The program has outlined a multi-mission approach, starting with Artemis I, an uncrewed test flight of the Space Launch System, SLS, and the Orion spacecraft. Artemis II will follow with a crewed flyby of the Moon, setting the stage for Artemis III, which aims to land humans on the lunar South Pole by 2025. What makes Artemis particularly groundbreaking is its emphasis on sustainability. Unlike the Apollo missions, which were short-term ventures, Artemis aims to build infrastructure that allows extended stays and facilitates long-term research. The Lunar Gateway, a space station orbiting the Moon, will serve as a hub for astronauts and missions, providing a launchpad for further exploration. The focus on the South Pole, rich in water ice, highlights the program's commitment to leveraging in-situ resources to sustain human activities. Meanwhile, China's Chang'e program has been making significant strides in lunar exploration. With milestones like the first-ever landing on the Moon's far side, Chang'e 4, and the return of lunar samples, Chang'e 5, China has demonstrated its technological prowess. The Chang'e 6, 7, and 8 missions aim to explore the South Pole and lay the groundwork for a lunar research station by 2030, potentially in collaboration with Russia. The synergy between robotic and crewed missions showcases China's holistic approach to lunar exploration. Russia, a veteran in space exploration, has also renewed its lunar ambitions. The Lunar series, with missions like Lunar 25, aims to map lunar resources and test landing technologies. Collaborative efforts with China further underscore Russia's focus on leveraging partnerships to achieve its goals. In Europe, the European Space Agency, ESA, has proposed the Moon Village concept, emphasizing international collaboration. ESA's involvement in the Lunar Gateway and its plans to develop technologies for sustainable exploration reflect its commitment to fostering global partnerships. Similarly, India's Chandrayaan program continues to make headlines, with the success of Chandrayaan-3 positioning the nation as a significant player in lunar science. Future missions aim to expand on these findings, potentially leading to crewed missions by the 2030s. Emerging space nations like South Korea and the UAE are also making their mark. South Korea's Danuri mission has provided valuable insights into the Moon's shadowed regions, while the UAE's early-stage lunar concepts signal growing interest from the Middle East. The rise of private companies has revolutionized the landscape of lunar exploration. SpaceX, with its reusable Starship spacecraft, is a key partner in NASA's Artemis program. Starship's potential to deliver cargo and crew to the Moon and beyond aligns with SpaceX's vision of making humanity a multiplanetary species. Blue Origin, another major player, is developing the Blue Moon lander, designed to transport payloads and astronauts to the lunar surface. Both companies are setting benchmarks for cost-effective and sustainable space exploration. Smaller companies like Astrobotic and Intuitive Machines are also contributing to lunar exploration through NASA's Commercial Lunar Payload Services (CLPS) program. Their robotic landers will deliver scientific instruments and technology demonstrations to the Moon, enabling critical research and resource prospecting. The interest in lunar resources, such as helium-3 and water ice, has sparked discussions about the lunar economy. Startups are exploring ways to mine these resources, while private investments are flowing into technologies that could make lunar tourism and colonization viable. Companies envision luxury lunar trips, cargo deliveries, and even infrastructure development, laying the foundation for a robust lunar economy. The Moon's resources and strategic importance have raised questions about international collaboration and competition. The Outer Space Treaty, OST, signed in 1967, prohibits the appropriation of celestial bodies and promotes the peaceful use of outer space. However, it does not explicitly address resource extraction, leading to debates over mining rights. The absence of a clear legal framework has sparked concerns about a first-come, first-served approach, potentially leading to conflicts over resource-rich areas like the South Pole. Efforts to address these gaps include the Artemis Accords, a set of bilateral agreements led by NASA to establish norms for sustainable space exploration. While many nations have signed the accords, countries like China and Russia have expressed reservations, citing concerns about exclusivity. The potential for competition over lunar resources underscores the need for robust international governance. Advances in technology are redefining the possibilities of lunar exploration. Artificial intelligence, AI, is playing a pivotal role in mission planning, enabling autonomous decision-making for rovers and landers. AI-powered systems can analyze data in real time, adapt to changing conditions, and perform tasks with minimal human intervention. Robotics is another game-changer. Modular robotic systems are being developed for tasks like assembling habitats, mining resources, and maintaining infrastructure. These robots can operate in extreme environments, reducing risks for human explorers. Innovations in propulsion systems are making lunar missions more efficient. Nuclear thermal propulsion, for instance, offers faster transit times, while solar electric propulsion provides cost-effective solutions for cargo delivery. These advancements are crucial for establishing supply chains between Earth and the Moon. 3D printing is emerging as a cornerstone of lunar infrastructure. By using regolith to create building materials, 3D printing can reduce the need for Earth-based supplies. This technology is being explored for constructing habitats, roads, and even landing pads. Communication systems are also evolving to support lunar operations. High-bandwidth networks and relay satellites ensure seamless connectivity, enabling real-time data transmission and collaboration between Earth and the Moon. Lunar exploration offers unparalleled scientific opportunities. The Moon's far side, shielded from Earth's radio interference, is an ideal location for radio astronomy. Telescopes placed here could observe deep space phenomena with unprecedented clarity, advancing our understanding of the universe. Geological studies of the Moon's surface and interior can reveal insights into its formation and the early solar system. The discovery of ancient volcanic activity and prebiotic chemistry could even inform the search for life on other planets. The Moon also serves as a testing ground for human factors research. Understanding how humans adapt to its environment will provide valuable insights for future missions to Mars and beyond. Studies on life support systems, medical protocols, and psychological resilience are critical for ensuring the success of long-duration space missions. The potential for a lunar economy is increasingly becoming a reality. The Moon's abundant sunlight makes it an excellent location for solar energy production. Helium-3, a rare isotope, could be a game-changer for clean fusion energy. Water ice, meanwhile, can be converted into hydrogen and oxygen for rocket fuel, reducing reliance on Earth-based resources. Lunar tourism is also on the horizon. Companies envision a future where people can experience the Moon's stark beauty firsthand. However, this raises ethical questions about preserving iconic sites like the Apollo landing zones. The Moon has all the makings of a portal into deeper space. To test techniques and technology for interplanetary travel, the Lunar Gateway will function as a center for trips to Mars and beyond. A new era in human history will begin with the permanent colonization of the Moon, turning it into a stepping stone to the stars. The mission to land humans on the Moon has evolved into a global partnership, including public and commercial entities from across the world. Although there are still obstacles, progress in technology, collaborations, and resource management is clearing the path for a long-term Moon presence. The Moon as a stepping stone to Mars, preparing for humanity's next giant leap. For a long time, the Moon has symbolized humanity's aspirations to explore other planets. It would be a great place to try out ideas and technology that may send humans to Mars in the future, because of its unusual environment, plenty of resources, and closeness to Earth. Nevertheless, the Moon provides an essential stepping stone to conquer the immense obstacles of establishing and maintaining life on Mars, in addition to its function as a celestial neighbor. The Moon is more than just a stepping stone. It is a testing ground for humanity's future in space, and we can learn more about this by looking at how lunar exploration helps Mars-bound missions. The Moon's harsh, alien atmosphere is one of its best advantages for Mars preparation. We can learn a lot about creating technology that can withstand and even thrive in harsh settings by studying the Moon, even though it isn't exactly like Mars. Similar to Mars, the icy, airless Moon surface poses risks such as radiation exposure, severe temperatures, and an absence of atmospheric protection. Technologies essential for Martian exploration, like autonomous robots, radiation shielding, and enhanced life support systems, may be fine-tuned by testing survival tactics on the Moon. Resource utilization is another key area where the Moon serves as a precursor to Mars missions. The concept of in-situ resource utilization, ISRU, which involves extracting and using local materials to support human activities, is vital for reducing the logistical burden of carrying everything from Earth. On the Moon, extracting water from permanently shadowed regions and using regolith to produce oxygen or building materials are foundational steps toward mastering ISRU techniques. These techniques can later be adapted to Mars, where similar challenges of resource scarcity and hostile conditions await. The Moon also offers a unique opportunity to study partial gravity environments. With gravity roughly 1/6 that of Earth, the Moon serves as an intermediate step between Earth's gravity and Mars's, tilde 1/3 of Earth's gravity. Understanding how human physiology adapts to reduced gravity is critical for ensuring the health and performance of astronauts on long-duration missions. Experiments conducted on the Moon provide insight into muscle and bone loss, cardiovascular changes, and psychological impacts, all of which will inform medical and operational protocols for Mars. Beyond physiological studies, the Moon enables comprehensive testing of habitat construction techniques. Building sustainable shelters on the Moon's surface allows engineers to experiment with materials and methods that could later be deployed on Mars. Technologies such as 3D printing using regolith, lunarcrete construction, and modular habitat designs offer promising solutions for creating self-sustaining bases. These innovations reduce reliance on Earth-based supply chains and lay the groundwork for constructing durable Martian settlements capable of withstanding extreme conditions. Energy solutions developed for the Moon also hold promise for Mars missions. Solar power, while effective on Earth and the Moon, becomes more challenging on Mars due to its greater distance from the Sun and frequent dust storms. The Moon provides an excellent testing ground for alternative energy sources, such as nuclear power systems like small modular reactors and radioisotope thermoelectric generators, RTGs. These systems are critical for ensuring reliable power on Mars, where energy demands for life support, research, and mobility will be substantial. Mars-bound technologies can also benefit from rigorous testing in the Moon's unique environment. Entry, descent, and landing systems for spacecraft, some of the most complex and high-risk components of Mars missions, can be refined through lunar trials. Precision landing technologies, autonomous navigation, and rover mobility systems are just a few examples of innovations that can be perfected on the Moon before being deployed on Mars. The Moon's regolith and rugged terrain offer ideal conditions to simulate Martian challenges and develop robust solutions. Lunar exploration further serves as a psychological and operational training ground for the human aspect of Mars missions. The isolation, confinement, and communication delays faced by astronauts on the Moon mirror the conditions they will experience during long-duration missions to Mars. Studying how astronauts cope with these challenges provides critical data for designing support systems and workflows that prioritize mental health and team dynamics. Training crews in lunar habitats also helps refine operational procedures, ensuring smooth coordination and decision-making under stressful conditions. The Moon's role as a logistical hub cannot be overstated. Establishing fuel production facilities on the Moon, using water ice to create hydrogen and oxygen propellant, opens up new possibilities for cost-effective Mars missions. Launching spacecraft from the Moon's lower gravity well significantly reduces energy requirements, making the transportation of supplies and equipment more efficient. A lunar staging point could also serve as a refueling station, enabling reusable spacecraft to travel between Earth, the Moon, and Mars with unprecedented efficiency. In addition to its technical contributions, the Moon plays a pivotal role in fostering international collaboration and advancing space exploration governance. As countries and private companies invest in lunar infrastructure, the Moon becomes a testing ground for cooperative efforts that could set the stage for multinational Mars missions. Shared lunar missions build trust, establish norms, and create opportunities for pooling resources and expertise. This spirit of collaboration is essential for tackling the enormous logistical, financial, and scientific challenges of reaching Mars. Private companies, too, are emerging as key players in this lunar-to-Mars pipeline. Innovations driven by the commercial space sector, from reusable rockets to advanced robotics, are accelerating the pace of exploration and reducing costs. Partnerships between government agencies and private enterprises offer a model for sustainable exploration, combining public funding with private ingenuity. As these partnerships mature, they create a robust ecosystem for developing the technologies and infrastructure needed to make Mars exploration a reality. The Moon also provides a platform for advancing scientific research that directly informs Martian exploration. Observatories and instruments placed on the Moon can study Mars, its atmosphere, and its moons in unprecedented detail. Lunar missions also offer opportunities to study impact craters, volcanic activity, and other geological features that provide analogues for Martian terrain. These studies deepen our understanding of planetary processes and help refine hypotheses about Mars's history and potential habitability. Aspirations for human space travel are symbolized by the Moon's position as a stepping stone to Mars. With each obstacle conquered on the Moon, we inch closer to our ultimate goal of setting foot on Mars. The Moon is a physical symbol of the potential that exists when people from all around the world work together to advance human understanding and technology. It stands as a representation of the insatiable human need to know more about the world around. Humanity refines the abilities, technology, and tactics necessary for interplanetary exploration on the Moon, which is more than just a stopover on the road to Mars. We can tackle the obstacles of Mars exploration more confidently and efficiently by taking advantage of the Moon's special environment, resources, and closeness to Earth. Don't forget to subscribe to our channel for more deep dives into the wonders of space. Thank you for watching, and until next time, keep looking up.